Going on to topic 3 of chapter 8, we're going to continue our study of quadratic equations. And in the quadratic equation, we're going to particularly look at the discriminant and then writing equations from solutions. Now, just read this to yourself. It is sometimes enough to know what type of number a solution will be without actually solving the whole equation. From the quadratic equation formula, b squared minus 4ac. This is what is found under the radical sign, is known as the discriminant. Now, if you think a little bit about this, and as we see it here in the quadratic formula, it really depends what this is, what this evaluates to, as to the kinds of answers you're going to get when you use the quadratic formula. So if this is a number that is above, let's say, 0, greater than 0, you're going to get real number answers here. If it is the square root of 0, if this equals the square root of 0, then you're only going to get one answer because plus or minus 0 doesn't change anything. It's just going to be negative b over 2a is your one answer if the discriminant is 0. Now, how about if your discriminant is a negative number? Then, instead of getting real numbers, they will be imaginary and, in a sense, complex numbers. So your discriminant determines all of this. Will your answers be real? Will they be just one real answer? Or will there be two imaginary, that is, complex number answers? And that's what this is about. So on this slide, we see the kinds of things they're reviewing. And if your discriminant is 0, then we get the same solution in a sense twice. So it would be one solution. If your discriminant is positive, you could get rational numbers, that is, if it's a perfect square under the radical sign, or in this case, irrational. And if it's negative, you're going to get imaginary, in a sense, complex conjugates, because one's plus, one's minus. Okay, a lot of stuff on this page. So here they're asking us to determine the type and numbers of solutions and how many. So how do we do it? Well, basically, I think I can use what they have here. We're going to need to know A, we're going to need to know B, and C. And we can pick that right out of the formula, and here they are. And then we just substitute B squared minus 4A, which is 4C. So our discriminant then, when we work it, comes out to a negative 15. This is going to be under the radical. So a negative number under the radical. There are two imaginary number solutions that are complex conjugates of each other. So you're going to have a first part, then plus something, a first part, minus something. And how about this one? Again, basically, you're going to try to identify, or you must identify, the A, it's in standard form, the B, and the C. Again, there they are. And the key is it must be in standard form first, so that you can correctly identify these letters. Put them into the discriminant, and here it's going to equal 0. Having it equal 0 means there's just going to be, well, actually there's 2, but in a sense 1 that are the same as answers to your quadratic formula. And by the way, anytime you get one like this can be solved by factoring. Okay, and let's take a look at this one. Okay, A, B, C, it's in standard form. Substitute and you get a 73. Now this is not a perfect square, so you're going to get positive numbers. That is not a perfect square. There you go. Thus, there are two irrational solutions that are conjugates of each other. All right, writing equations from solutions. Now, this is working backwards. Here, we know that the principle of the zero products state that if you have this factor and this factor, and they equal 0, then this equals 0, x is going to equal a positive 1. And here, this equals 0, x will equal a negative 4. Well, if we know what our solutions are, we can go back and put them in this factored form, opposite signs. And then we can FOIL this, and we get our original trinomial that is in standard form. So let's see some here. And I'll work this out with you. I like to work these out too. So basically, we're going to set something up like so. And we know that there's going to be an x there, and there's going to be an x there. And here there's going to be opposite signs, a negative 5. Now here's where it's a little tricky. We know that this is going to be a positive 4, opposite sign there. But where does that 3 go? That 3 goes right there. So that if this equals 0, the 4 comes over as a negative 4 divided by 3. Okay? And perhaps I should have done it this way. That x equals 5, x equals a negative 4/3. Now, a step backward would be that this 3 goes over there, and then this 4 goes over there, opposite signs, and that's where I got that from. Now this one is just opposite sign. And then we FOIL this, and that gives us 3 x squared. Our outers are 4x, inners a negative 15, so it looks like our inners are a negative 11x, and our last term is a negative 20. And it's working backwards, which I think is a good thing. So, okay, they're starting it this way. And reverse signs. Oh, I don't like this one here, but that's okay. And it's going to be this. And it's kind of, well, again, I'm not too crazy about this way here. But when they FOIL it, they do get the correct answer. Okay. So just bring this 3, and again, if they put it properly, it's easier to figure out. The 3 goes there, and the 4 goes there. Okay. How about this one? And let's work this one out. So again, the way I would do it, I would just jump right to this step here. So the strategy would be, this is going to be x here, x there, and it's going to be opposite signs. So negative 3i. Here, this will be a positive 3i. So in a sense, we have conjugates that we're going to FOIL. And this gives you x squared. Now this is going to give you a negative 9i squared. And again, multiplying conjugates, you get the difference of perfect squares. But you have to remember that anytime you have anytime you have I squared, that's a negative 1. So this becomes x squared plus 9 equals 0. So we had said throughout math, the early parts, that the sum of perfect squares is not factorable. That's true because it's not a real number answer, but it is factorable if you use imaginary numbers. Okay, so that's that. Let's check it out. Okay, they're putting that step in that we know already. Then you just transpose those, equal to 0. And there are your conjugates. And then if they FOIL the conjugates, here they're showing you that the inner terms cancel out, and you end up with this. Okay. Well, again, there are lots of examples that I do in the additional exercises if you'd like to see more of this worked out.